Hey everybody, it's Mr. Clausen. I just wanted to do a quick screencast here on the trends from the periodic table. When we tried in class today, didn't work so well, so I tried to put something together a little bit better. Now what I want you to take a look at is by the end of this screencast here, what we're going to go through is what patterns you can find on the periodic table, and the trends I want us to look for are mass, atomic number, or the number of protons, where the valence electrons are located, reactivity, and then finally radius. So what I want us to do here real quick is just kind of keep that in mind where we go through. Now atomic mass and atomic number we probably already know. It's pretty easy as you go from left to right on the periodic table. So as we go across this way, it's real easy to see that it goes from 3 to 4 to 5 to 6 and so on. And then also if you take a look at the masses get bigger because if you add protons, you're also going to add neutrons as well in order for it to be stable, and the numbers go up. So both atomic mass and atomic number follow this general trend where if you go to the right or you go down, they're both going to increase. Okay? All right. Now, if you take a look at the valence electrons, that's the other one I'd want us to take a look at. And we've kind of learned that valence electrons, remember, are just the outer electrons that are available in the atom. And they're the ones that really determine what's going to happen with the element. So group 1 all has 1 valence electron. Group 2 has 2 valence electrons. And I told you to kind of not worry so much about the idea of valence electrons here for the inner transition metals. We can skip over those for now. And the reason is things just get really complicated and the general patterns break down due to the increased number of energy levels that the periodic table has. So if you skip that, you then go to group 13, which has 3 valence electrons. You get 4 valence, 5, 6, 7, and then the noble gases, this is really important, they have 8 valence electrons. Now remember, we consider 8 to be a full outer shell. Now it's important to notice that not every noble gas has 8 valence electrons, because if you take a look here, there's one that's very particular, helium, it only has 2 valence electrons. So a better way of saying it is, they have a full outer shell for the noble gases, but a general thing for most of them, the neon, argon, all the way down to the bottom here, they're going to have 8 valence electrons, just with helium being the exception because it only has 2 to complete that shell. All right, now the one that gets a little confusing here for us is atomic radius, which now that I bring it up, I realize we're going to talk about that second. What I have set up here is for us to talk about the reactivity and how that works. Now, in class, we brought up this idea that the way you should think about the periodic table is more like a map, right? And so it's not like you have just the left side and the right side. The way to think about this is the periodic is just a continuation. So you go, 1, 2, and then once you get to 2 protons, where do you go when you go to the third one? Well, you start back down here on the next level, 3, 4, 5, 6, 7, 10, and then you go to the next one over. And so really what's happening is anytime you get to the end of the periodic table, quote unquote, here with the noble gases, when you extend beyond, you don't just fall off. Really what you end up doing is showing up at the other side. So the periodic table is really just a continuous thing. Think about it kind of like a map, like we said. When you get to one end of the map, you just show up on the other side. The periodic table to have some different proposed shapes over the years, and here's 2 of them that you can take a look at. So if you take a look, it starts with hydrogen in the middle, and then what it does is just spirals outward, and you get this thing where it never really ends, and this takes in the transition metals. And the important thing to note here is that this yellow part, that is the noble gases that we saw before, okay? So that's one way to do it, or there's this other illustration that I found too, same deal, you start in the middle, and you just it just spirals itself around, and the groups still happen by color, but you just keep going around and around and around, and it goes to it. So what does this mean? Well, remember for reactivity that the noble gases are unreactive, and that's why they're called the noble gases. They do not, in general, form bonds with anything. And the reason for this is they've already got that 8 valence electrons or that full outer shell. Now, what this then means, though, is that the elements on either side of the noble gases, so for example, group 17 here, the halogens, and group number 1, which is the alkali metals, they are the ones you could consider to be on either side of the noble gases. So you take a look up here, remember noble gases. So here you go, here's group 1, and here's the ones on the other side. That's group 17, or the halogens. Now what that means is they are so close to having a full outer shell. The halogens have 7 valence electrons, and group 1 has 1 valence electron. So it's very easy here for the halogens who have their outer shell full to just steal an electron from somebody else, giving them the 8, and they will do this any way they can, and that allows them to form bonds with anything. Or, for example, group 1 over here, they have only 1 valence electron, and so what they often try to do is they try to take their 1 electron and give it away to anybody else, and this also allows them to form bonds. But it turns out that the 2 extreme sides that I have here are the ones that are the most reactive. So the first trend when it comes to reactivity is for nonmetals, which we divvy up right around there, are more reactive as you go to group 17, and metals are more reactive as you move your way to group 1. Now, as you saw in laboratory with Mr. Welch, there are some other trends here too. And as you go down a group, they will also become more reactive. So that means more reactive. So the most reactive element that exists for metals is francium down here at the bottom. And now nonmetals, just like the name says, they are non-metals. They are the opposite of metals, and so the pattern is just reversed, with the one that wants to grab electrons the most and therefore is the most reactive is fluorine. All right, so those are the trends there. So in general, the closer you get to group 18 or the noble gases, the more reactive something is, and then there is a trend going up or down as well. Now, the next one I wanted us to talk about here was atomic radius, and it's a little bit confusing at first. And we saw this graph in class, and I just didn't have enough time to go through it for what I wanted to know. But the first thing is atomic radius really just means this. So think of the atom like a circle or a sphere, and the atomic radius is just the distance from the center to the outside. So essentially, atomic radius is really just talking about the size of each individual atom. So if we take the sizes of the atoms and we put them on a graph and we have them go from atomic numbers, so no protons whatsoever, all the way up to 110 protons over here, what you get is this pattern. And it's not a nice, easy pattern that you see anymore. You would think that, by increasing the number of protons, the size would get bigger. And while that's true, there's this general overall pattern that the graph is starting to move its way up, and so the atoms are getting bigger. Really what you want to notice is the fact that there are these drastic spikes, and then it gets smaller, 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 and then there's another spike. And while it looks confusing at first, I'm here to try and help explain this to you a little bit better so we can understand it. What you really want to take a look at when you're trying to figure out what's going on here with the pattern is take a look at what elements are at the top of the spikes as well as what elements are at the bottom or the base of the spikes. So the ones I'm going to start with are the ones that are at the top of the spikes: helium, lithium, sodium, potassium, rubidium, cesium, francium. If you think back, you guys should ask yourself, okay, where have I seen those before? And you're right, they're all the ones from the group 1. So if you take a look, here's hydrogen, hydrogen, lithium, lithium, sodium, sodium, potassium. And I don't need to keep doing this. I'll allow you to be able to follow along with me. But if you take a look, all the ones that are at the top of the spikes are the group 1 metals. Now let's take a look at the other ones. What are the ones that are at the bottom of all the spikes? Okay. Helium, neon, argon, krypton. Those are the ones that you find over here. Now, what does that mean? That means in any given row, what we end up seeing is that the red ones here are very large, and then as you go across the table, so let's take a look here, we'll start with lithium. As you go across the table, what's happening is the atoms start to get smaller and smaller and smaller and smaller and smaller until you finally get to neon right there, neon being the smallest one, and when we go to the next level, all of a sudden, boom, there's this big jump in size. Now, the reason for that isn't as complicated as you might think. Just remind yourself what is happening over here whenever we get to the bottom of one of these spikes. So when we're at one of the noble gases, what's happening with the noble gases? Remember, the noble gases now have a full outer shell. They have those 8 valence electrons. And the next electron that's being added to it has to go somewhere, but it can't go in the current shell. So what happens? It ends up being bumped up to the very next energy level. And if you take a look, that's what happens. So you go from a noble gas argon, you add one more electron to it. It cannot fit in this energy level anymore. So what happens? They have to make a brand new energy level to that. So that's why we get those big spikes. Now, this reason here is a little bit harder to understand, and we'll go to the next slide for us to see what that actually looks like. So if you take a look here, what they have is that trend drawn out. You get a good visualization of showing what's going on with the size of each atom. If you take a look, it's very easy to see that as we go from left to right, they are starting to get smaller, which is just what that graph showed us, right? And also, as you go down the table, you can see that the atoms are getting bigger. Now, that should be pretty straightforward. As you go down, there's more protons, there's more energy levels, so of course they're going to get bigger. But the part I wanted to talk about is why, as you go this way, do they end up getting smaller and smaller and smaller until you get the smallest one at that energy level over here in the noble gases. Well, remember what makes up an atom. You got protons over here in the nucleus, and then you've also got electrons floating around outside here in energy levels. So I'm trying to draw here, that's the first energy level, so you got 2 electrons, and then you go to the next energy level, you can fit 1 more. So this would be an example of what lithium would look like. Well, protons are positive, and they're going to attract the negative electrons. Now what's going to happen if we add another proton over here? Well, what this does is it adds another electron. But what happens to the amount of force that's pulling them together? Well, by adding another electron and another proton, this pull that's pulling the two together is a little bit bigger, so these outer electrons aren't quite where they are there. They end up scooting in just a little bit, ever so much. If you add another proton, the pull is just a little bit bigger, pulling everything together. And so by putting another electron out there, what happens now? It ends up pulling it in a little bit more. And this continues to go on until you get your 8 electrons. I don't know what we've got there, 6, we'll squeeze a few more in, 7, 8, until everything is full. And then eventually you're going to want to add 1 more, and the diagram isn't full. So what happens when you add another proton, you add another electron, and what this does is it gives you a big, another energy level. And that's why it's this additional energy level, which would be the single valence electron, which we see in group 1, why we get that big jump in size. The fact that they get smaller and smaller and smaller is because as you add electrons, there's more pull pulling them together, and squeezes it that way. About a lot, so what we got to do here is we just got to put this together into a final trend. So atomic radius, what I've shown you here is the arrows show how everything is increasing. So as you go down the periodic table, the size of the atom is going to get bigger. And we talked about how as you go from left to right, it actually gets smaller, or the other way you'd say this is as you go from right to left, the atoms get bigger. Okay? Now, it turns out that this trend is opposite of the other trends that we saw. So what you got going on here, we have mass gets bigger and atomic number gets bigger. So as you move from left to right, you increase the mass. And as you go down, you also increase both the mass and the mass number. Next trend I want us to take a look at here, I've added some atoms. And what I want us to do is just look at how the valence electrons would show up in each one of these cases. So the trend for valence electrons, remember that's the same for an entire group. So if I draw the picture here, it's the same for all the elements in that group all the way down. So let's take a look here. How many valence electrons do the first group have? Well, they have 1. Well, group 2, how many do they get? They get 2. Told you to skip because things get weird here in the middle. And the pattern then comes over here. Group 13, it has 3 valence electrons. Group 14, 4, 5, 6, 7, and then finally, the noble gases, we've talked about this before, has 8 valence electrons, or a complete shell. And that's why, once again, when you go to the very next level, so once you continue on here and you go all the way over to the other side, you draw another atom. It's got another energy level, so it's going to be a little bit bigger, but it's still only going to have 1 valence electron in its outer shell. Now, this is the reason for why we see the trends in reactivity that we do. Remember, we talked about group 1 here. It's very easy for it to remove its electrons. And over here, it's very easy for fluorine to steal an electron, or actually anything from the halogens. It's very easy to steal an electron from somewhere else. Now, the only ones that are not reactive is the group 18, because they have that full valence outer shell, so they're not going to react with anything because they don't need to get the electrons from anyone. If you wanted to take a look here at a trend, we got this trend like so, with reactivity increasing as you go to the lower left-hand corner for the metals, and then going to the upper right-hand corner for the nonmetals, although I think I circled the wrong one. Remember, these ones are not reactive. Fluorine is the most reactive. The one next to it, neon, isn't going to react with anything. So there it is. There's all the trends of the periodic table. Hopefully this helps, and I will see you on Monday.